Hello everyone. Starting today, we will start a new part of the course where we move beyond reactive methods such as wall following and follow the gap. Over the next two sessions, we will cover localization and mapping. And in particular, we will cover a specific approach to localization and mapping called scan matching. In today's lecture, I will introduce the concept of localization and the motivation behind it, as well as the specific approach to localization using scan matching called the point-to-line ICP algorithm, presented by Sensi et al. In 2009. So far in the course, we've constructed the robot and learned how to give basic commands in order to move our robot. So we also learned about PID control in the context of tuning the VEST controller, and by doing so, we fine-tuned movement and the reactions to our commands. Some of the first algorithms that we've covered are wall following and other reactive methods, which utilize sensor data given from the LiDAR. We call follow the gap and wall following reactive methods in the sense that it reacts to the local frame of reference, or whatever the robot detects at the current state. And based off of these methods, we also had our first autonomous race. So what comes next? Since we know how to control the robots without our instruction, and they're able to move and navigate through some track, are we now ready to deploy them out into the wild? The answer is obviously no. What would happen with only wall following and follow the gap in the following example? What you see on the right is an image of the Levine building lobby. And as you can see, it has an open space and a track that is drawn in the center. Using only wall following and follow the gap, it's most likely that the robot will not be able to follow this desired track and will probably go into some of the open spaces. Now, in order to resolve this issue, the first step would be to find a way for the robot to find its position within this given map. This is precisely the problem of localization, which we focus on in today's lecture. More formally, the problem of localization is to determine the state, the position, and orientation of a robot with respect to its environment. Now, the environment can include some landmarks which are known or unknown. Localization can be done within a global frame of reference of a map, or it can simply be relative to one starting point. In other words, let's say that a robot is given some initial position, and then after some time, it moves in some direction. You'd want to know how far to the left or right, or in whatever direction that the robot moves, relative to this initial starting point. The reason why we focus on localization first is because localization is a key component of all the methods in the course moving forward. Some examples of using localization is the tracking problem, where in this example, you can see a red line being traced on the map as the robot is navigating through the halls of the building. In this case, we are actually given the map, and the problem is to localize and find one's position in the map efficiently. In this particular video, you can see how the trajectory of the robot is being traced very, very efficiently. And this is used through a method called particle filtering, which we'll cover later on in the course. In another situation, there are examples where the map is unavailable and the robot is required to create the map while also determining its location within the map. This is the problem of simultaneous localization and mapping, or SLAM. Now, in this particular example, the robot is using a system for SLAM by Google called Cartographer, which we'll learn about later in this course. Now, in the lower segment of the video, you can see the robot moving along the hallway and creating a map based off the LiDAR measurements shown in red. However, you can notice how the hallway is slanted, but then when the robot reaches the end of the hallway, it recognizes the corner as something that it's seen before, and therefore is able to correct itself. This is a feature called loop closure and is an important concept that we'll cover when we go into detail about SLAM algorithms later in the course. However, these two examples kind of highlight some of the issues that we can run into while trying to solve the localization problem. Now, we want to be able to locate our position with reference to our initial starting point. And so in our first attempt for localization, we utilize odometry and motion integration. Odometry attempts to localize by starting at a known pose and position and integrate the control and motion measurements to estimate the current pose. In the case of our robot, we can integrate the dynamics using the information from the VESC and the wheel encoders and other sources of information such as the IMU. How this works is that when we give the commands for movement, this is used by the VESC unit and translated into lower level commands that control the acceleration and deceleration of the robot. The VESC keeps track of the acceleration that is achieved, and this is integrated to obtain the velocity. And finally, the velocity is integrated to give us the amount of movement since the robot first started. The issue is that noise occurs at all stages of these measurements. And so there could be some error in the velocity measurement, for example. And so perhaps the velocity is measured at 4.1 meters per second when it actually is 4.2 meters per second. In this case, the robot will have actually traveled farther than it has perceived. Now, having better equipment will no doubt help. However, there is a fundamental limitation to using odometry alone, as it is an open loop estimation approach and there is no feedback mechanism that allows for us to correct for errors in the measurement. Therefore, if there is noise in the measurements, this error will accumulate and increase over time. To get a better understanding of this, let's say that we know our robot is starting at some initial point, as shown in the middle of the slide. We can give it a command to move to the left for a certain amount of time to arrive at the position circled in red. The small group of points represent the distribution of possible positions of the robot by accounting for the error that can occur in the measurement. How spread out this group of points is represents the uncertainty in our position. Notice how the uncertainty increases if we continue to move in the same direction, and the spread of the point increases. This becomes more prominent as we tell the robot to turn and proceed downwards. And after a final turn and proceeding forward for a longer period of time, notice how the possible positions are now so spread out that we're not able to determine the correct position of the robot. Using odometry for localization is known as dead reckoning in aircraft and maritime navigation. And many approaches have been explored to overcome some of the limitations that we've seen of open loop estimation. And so one of the basic approaches is to utilize another source of information. And in our case, we have range sensor measurements provided by LiDAR, which are extremely accurate compared to the inertial sensors, such as the IMU. This brings us to the next approach explored in this lecture, which utilizes scan matching, which we cover next. Scan matching is one particular form of localization. And compared to other methods of localization, scan matching attempts to localize using a set of range measurements collected across time. For the F110 car, this corresponds to the LiDAR information that is collected as the robot progresses. One thing to note in this particular version of scan matching, we don't utilize the odometry information. However, in other versions, the output of scan matching can be combined with odometry information in order to improve localization. In order to better understand the problem, let's start with a simple example. Let's say that my robot is in some environment with the landmarks A, B, and C. Now, these landmarks A, B, and C are fixed within the global time frame. And therefore, at time t equals to 0, if measurements of the distance to A, B, C are taken, their positions can be localized accordingly as shown on the right. Note that since we know the actual landmarks, we are able to approximate the reference surface formed by the relative positions of A, B, and C, as indicated by the line segments connecting A, B, and C. The robot itself has its own local frame of reference, where we place the origin of the reference at the center line between the two rear points of the body. In the F110 car, this would be the center of the axis connecting the two rear wheel tires. At time t equals 0, the measurements to the different landmarks can be shown within the local frame of the robot. At time t equal to 1, we assume that the robot has been moving in some unknown direction for some time. And so because of this, the distances to the landmarks will have changed. And so if we take the measurements to the landmarks A, B, and C once again, we'll find that they have changed in position as shown here. The scan matching problem is to find the transform R that will transform the set of points measured at time step t equals to 1 to be close to the set of points measured at time step t equal to 0. The reason why we want to do this is because the amount required to translate the set of points to match and minimize the distance between these sets of points is exactly how much the robot has moved in time between time steps t equals to 0 and 1. Therefore, the goal of scan matching is to find this transformation R, consisting of a translation and a rotation, in order to localize within the local frame. Now, if we knew exactly where these ABC landmarks are, then this problem would not be very difficult. However, in general, we don't know which measurement corresponds to which landmark, and therefore, we need to find a different solution. So the approach that we actually take is that we assume that the closest points will be corresponding to each other, a concept that we call correspondence match. And based off of these correspondence matches, we will iteratively find the best transform R. So the way that the iterative algorithm works is that you make some initial guess of R, which we call the current guess. And after transforming the points with respect to this guess of R, for each new point in the scan, we find the closest point in the previous set at time t equal to k, a process that we call the correspondence search. Now, based off of the correspondences, the algorithm will make another better guess of R and set this next guess to be the current guess and repeat steps 2 to 4 until it converges. Here, the key question is, how do we actually determine what is a better guess? And part of the answer is that we need to find some sort of metric, which we call a match function, in order to determine what is a better guess. In order to explain what I mean by a better transform, we can take this example where we are trying to transform the set of points at t equal to 1 to a local reference frame at t equal to 0. Let's say that we have one option, shown in purple, that transforms the points at t equal to 1 to some direction to the left, and another option that transforms the points to the right, as shown in orange. The question becomes, how do you actually choose between the transform 1 and transform 2? In this example, the obvious answer is option 2, But that's because we know the points correspond to A, B, and C. And it's obvious that the points at time step 1 end up closer to the points at time step 0 when they are transformed. Even so, we'd like to be able to determine this more objectively and use some metric to quantify the distance between the corresponding points. A naive metric would be to simply sum up the distance between the corresponding points. Since in this case, we actually know the corresponding points, if we sum up the distances between the corresponding points, we'll be able to determine that transform 2 results in a smaller value in terms of the metric, and therefore is the better transform. However, this method will actually break down when these correspondences are unknown, and will be very sensitive to noise in the measurements, and therefore is not very robust. A better metric function would be to use what's called the point to projected point or point to point metric. How this works can be shown through the example. For example, the closest point to B is going to be the point 3. We find the projected point on the line segment 2 to 3, the distance, which is B prime. We similarly find these projected distances and square them and sum the squares of these projected distances and achieve the score A prime squared plus B prime squared plus C prime squared. Based off of this metric, you'll obtain a similar answer where the score for transform 1 will be much greater than the score from transform 2, and therefore you would choose transform 2 as the better transform. Now, this metric is used in an algorithm called the Iterative Closest Point Algorithm, or ICP algorithm. And in this algorithm, an initial guess of the transform is made, and the corresponding score of the transform is computed according to the point-to-point metric. In the next iteration, the algorithm improves the guess to reduce the value of this metric. It repeats iterations of this algorithm until it converges to a solution. One thing to note is that this ICP algorithm is a more general algorithm that can be used beyond for our purposes for the autonomous car. In this video, you can see how 2 point clouds of a 3D model of a rabbit are aligned using ICP. And in this way, whenever you have 2 sets of data points that need to be aligned, ICP can be an algorithm that can be applied. Now, when ICP algorithms are used in the context of localization for autonomous robots, we have an additional set of assumptions. The first being that it assumes that we have a sufficiently fast scan rate. And what this implies is that there will be significant overlap between the sequential scans, and so that points with high correspondence will always exist. Another assumption that's being made is that it assumes that the surface will be non-smooth and heterogeneous. The reason for this is because a smooth surface will actually look the same to the algorithm. To understand this, we can observe in this video showing the scans of a vehicle as it proceeds down a hallway. Since the hallway is very similar from the scan perspective, even though the vehicle is moving, it's unable to detect the movement. And it's only after a turn is it able to determine that, oh, some movement had occurred. And at this point, localization has failed. We will see how other methods of localization overcome these assumptions later on in the course. In addition, ICP has some other practical limitations. For instance, the initial guess of ICP is very important in order for it to converge. And moreover, the vanilla form of ICP can be slow, which we'll try to address in this lecture. This brings us to our main algorithm for the lecture, the point-to-line iterative closest point algorithm, or PLICP, presented by Andrea Sensi in 2009. Now, compared to the vanilla ICP algorithm, PLICP has two major improvements. The first is that instead of a point-to-point metric, it defines a point-to-line metric and uses that in order to score the different transforms. The second uh, set of improvements are some clever tricks with respect to the correspondence search. Now, in this first lecture, we'll be focusing on um, the actual point-to-line metric, and next time, we'll be focusing on the second set of improvements regarding the correspondence search. So the first major improvement of the PLICP algorithm is the change from the point-to-point metric to a point-to-line metric. So in order to understand how this improves the performance of scan matching, we will delve a little bit deeper into the definitions of both. Given a point in the current scan, PIW, and its corresponding line segment, PJ, 0 to 1, point-to-point measures the distance as the distance to the nearest point on the segment. So in other words, you take the point and project it onto some existing point on the line segment itself, as seen here. In comparison, point-to-line measures the distance as the distance to the nearest line containing the segment. So given the similar setup from before where we have the point PIW and the line segment PJ0 to PJ1, rather than projecting it onto the segment itself, we project it onto the line that contains this segment. And therefore, the distance is the perpendicular distance from the point to the line. And so there are certain cases when using the point-to-point metric and when using the point-to-line metric, the values may coincide, as seen here in the figures below. However, even in this case, the point-to-point metric projects onto a particular point on the nearest line segment, whereas the point-to-line is finding the distance to the nearest line. So understanding why the point-to-line metric improves the speed of the algorithm can be explained by two reasons. The first is that from the perspective of the one projected point, as can be seen in this figure, let's say that we have some reference surface S of ref, as shown in blue. For the point Pi of W and its corresponding projected point Pi, with the point-to-point metric, the contours of the level sets are concentric and centered at this projected point. In comparison, with the point-to-line metric, the contours of the level set are actual lines. This implies that the level sets of the point-to-line metric approximate the actual reference surface better when compared to the point-to-point metric. This in turn means that we have a more accurate approximation of the error. And having a more accurate approximation of the error means that we will have a faster convergence in terms of the algorithm itself. Now, the second reason why using the point-to-line metric is faster can be explained from the perspective of the space of transforms induced by the metrics. So let's assume that we have two sets of scans, one at time step t equal to k, and one at time step t equal to k plus 1. Here, please note that the ABC is simply signifying the index ordering for the points and is not related to the correspondence between the two sets of scans. Let's further assume that we are only searching over the set of transforms which are vertical translation of the points, meaning that we only move the points up or down. You can imagine that there are three possible transforms which can be found iteratively from the algorithm, beginning from the transform Q0, the transform Q1, which moves the set of points in t plus 1 closer to the to t equals to k with respect to the vertical axis. And finally, the transform Q2. Let's first use the point-to-point metric to evaluate these three transforms. So using the point-to-point metric, the point A and the transform Q0 the distance to the nearest projected line segment will be A0. And similarly, for point B, the distance to the nearest segment will be B0. And for point C, the nearest point will be C0. The score of transform Q0, according to the point-to-point metric, will be the squared sum of these segments, which we show here as d of Q0. We can make a similar computation for the remaining transforms. So if the score for Q0 is A0 squared plus B0 squared plus C0 squared, for Q1, the score will be A1 squared plus B1 squared plus C1 squared. And similarly, the score for Q2 will be A2 squared plus B2 squared plus C2 squared. Now, one thing to note here is that the closest point for point A with transform Q2 has changed to a different line segment. Now, the key thing to note is that the score for all of these three transforms are going to be different. And so from the perspective of an iterative algorithm that is searching through these possible transforms, each of these transforms are possible candidates which the algorithm needs to search over. Now let's compare the scores for the same transforms Q0, Q1, and Q2, but instead of using the point-to-point metric, let's use the point-to-line metric. For Q0, the point A is projected onto the nearest line, resulting in the distance A0 prime. And similarly, the distance from point B to the nearest line under the transformation in Q0 is B0 prime. And for point C, the distance is going to be C0 prime. And so the score under the point-to-line metric will be A0 prime squared plus B0 prime squared plus C0 prime squared. As before, if we compute the scores for the remaining transforms, Q1 will have a score of A1 prime squared plus B1 prime squared plus C1 prime squared. Now, the thing to note here is that under the point-to-line metric, the score for the transforms of Q0 and Q1 will be exactly the same. Now, we score Q2 in a similar fashion, and note that we are assuming that Q2 is at the threshold where the closest line to point A will change. Thus, in our example, we find that Q0 and Q1 will have the same score, while Q2 has a different score. And so, in fact, all the transforms from Q0 until Q2, which is at the threshold, will have the same score. This is important from the perspective of the iterative algorithm in that by using the point-to-line metric, since all the transforms starting from Q0 to Q2 will be the same, if an algorithm starts the search from the transform Q0, it will go directly to Q2 at the next iteration. This is illustrated in this figure from the original Sensi paper, where each point represents a possible transform in the space of transform. So, given some different initializations of these transforms, under the point-to-point metric, the algorithm will follow the trajectory where each point will result in a different point-to-point correspondence. In comparison, under the point-to-line metric, all the transforms within an area will have the same point-to-segment correspondences and will be considered equivalent. Therefore, intuitively, the space of transforms has to be searched over will be reduced, resulting in a faster convergence. So hopefully, the reasons explained until now has convinced you of the benefits of using the point-to-line metric in comparison to the point-to-point metric. And so now, as part of your lab, you will be implementing the Sensi algorithm. So I'll go over the overall structure of the algorithm and some key points for your understanding. But please note that there are some simplifications, and so I recommend you to refer to the step-by-step details in the lab and also the original paper. Now, the algorithm itself takes as an input a reference scan y of t minus 1, the current scan y of t, and then some initial guess of the roto transformation q0, which I will explain shortly. Given these inputs, the output of the algorithm is the transformation q, which is the converged solution representing the rotor transformation between the two scans at y, the two scans y of t minus 1 and yt. Now, at any given iteration of the algorithm t equal to k, we use the previous guess q of k to transform the coordinates of the current scan into the frame of the previous scan. And then for each point, we then find the closest line segment, which is the point-to-line correspondence search that we covered before. And then based off of these correspondences, we then update the transform in two steps, where we first formulate the point-to-line error objective, and then we find this next iteration of the transform q of k plus 1 that will minimize this objective. And we'll go into detail about this shortly. This algorithm will repeat until we converge to a particular solution. Now, in the remainder of this lecture, I will explain the details of this algorithm from the code's perspective, which you will need to implement in this lab. And so the main module that implements this algorithm is the scan processor and the scan match CPP file. In particular, you'll have to implement the handle laser scan function, which I'll explain next. The handle laser scan function is structured in the way that it uses the previous guess, q of k, to transform the coordinates of the current scan into the reference frame of the previous scan. This is indicated here in red in the code. Now, this transform q of k is a tuple t of k and theta k, where t of k is the translation in x and y, and theta k is the degree of rotation of the position. And so for the ith point, we define the roto translation operator r that and the translated point p of I of w, which is basically p of I that's been rotated by some theta value and translated by t of k. So p of I of w is the newly translated point within the reference frame of the previous scan. After this coordinate transform has occurred, the set of correspondences at iteration k is defined as c of k, where each element is some tuple that determines which line segment a point is closest to. Now, for this first part of the lab, we'll use a naive correspondence search, where you basically just do a exhaustive search of trying to find the closest line segment. But we will implement some improvements, which we'll cover next time, that will greatly make this correspondence match much more efficient. After the correspondences have been found, the transform is then updated in the update transform function. Now, to do this update, we first proceed by formulating the point-to-line metric objective shown here. Now, this may look very complicated, but in fact, we can understand this if we recall some basic vector geometry. So let's say that we're given the point pi of w and the line segment pj1 to pj2. If we want to be able to find the distance from the point to the line, we first have to we have to define what this distance is. And so in order to do this, we first define the vector A, which is the vector going between pj2, a point on the line segment, and piw. Next, the normal vector n of I is the vector that is perpendicular to this particular line segment. And the angle between these two vectors is theta. From vector geometry, we know that the inner product of n and a, or n transpose a, is the same as the transpose a of is the same as a transpose n, and by definition is the magnitude of a times the magnitude of n times cosine theta, the angle between them. Since the magnitude of the normal vector is 1, this ends up being a cosine theta. And so this inner product is exactly the distance from the point to the line that we desire to compute. So recalling the point to line metric objective here, for the ith point, we can see how this point is the translated point P of I of W. And this expression here is the same as our vector A, representing the vector between one point of the line segment and our transformed point. N of I is the normal vector for the line segment. And finally, this is the inner product which computes the distance from the transformed point to the line segment that is corresponding to that point. Thus, the objective is simply summing up all of these distances between the point of one set and the corresponding line segments. Now, given this objective, we then solve the optimization problem, which tries to minimize the objective function in order to obtain q of k plus 1, or the next best guess. And so more formally, the optimization problem minimizes over theta and t, which define this rotor transform q, in order to minimize the objective function j. Next, I'll go over briefly how the closed form solution for this problem is derived as it pertains to the implementation. But this portion may be a little bit difficult to understand on the first pass, and so I recommend reviewing the original paper for the full derivation. Now, in order to derive the solution, we first rewrite the objective by defining a few variables. First, we define pi of I to be p of ji, which is the corresponding point for the transformed point. We define the state vector x to represent the transformed q, where the components correspond to the translation in x and y, and also an equivalent expression for the angle theta using cosine and sine is obtained by setting the constraint x3 squared plus x4 squared is equal to 1. In addition, for each point pi, we define the matrix M of I as such, and also the matrix W, and similarly the matrix C of I. With some algebraic manipulation and using these definitions of the variables, we can rewrite the objective function as follows. I'll leave this derivation to the listener or student in order to as an exercise. Now, some of you who are familiar with convex optimization will recognize this as a quadratically constrained quadratic program. Now, I can't go into the details of convex optimization as an entire course can be dedicated to this topic alone, but I will provide some intuition behind how this problem is solved in order to obtain an optimal solution x in the general case. Now, imagine that our objective function is a convex function g of w, and we are searching over the domain of w. Directly finding the solution that minimizes this objective is often very difficult. And so instead, what we do is use an iterative process where we start from some initial guess w0, and approximate the objective function around this initial solution of W0, shown as the blue parabola that is that is intersecting the objective function at that point, at the point W0. The point which minimizes this approximation is found, which is W1, and is used as the starting point for the next iteration. This continues until eventually the algorithm converges to the optimal solution, W star. Now, the reason why we like to use convex functions and formulate a convex optimization problem is that for convex optimization problems, once you converge to an objective, the solution is guaranteed to be the global solution. Now, unfortunately, a quadratically constrained quadratic program is not convex in the general sense. So there are specific cases where it is convex, but generally they are not. And in this case, and especially for our problem, it's not a convex problem. And so the only guarantee that we have is that we have reached some local minima in terms of the solution. However, all is not lost in that scan matching itself is an iterative algorithm that solves for the next best solution. And at every iteration, fortunately, we have this closed form solution that makes the algorithm much more efficient. And so I will now go into the derivation of this closed form solution. But as before, I'll focus on how to implement the solution in code. And so the detailed derivation of the solution can actually be found in the paper. Now, in order to find the solution to the optimization problem, which we derived before, we implement the computations in the update transform function. The first step is to define the M's, C, and W matrices for the objective function and the constraint. Note that we're using the C++ library eigen in order to define these matrices and the matrix observations. Now, by expanding out the expression of the objective function and regrouping according to the X, we can define the matrices M and G and rewrite the objective in terms of M, W, and G. Now, this is implemented in the sections of skeleton code indicated on the right, and this is part of the exercise that you will have to go through during the lab. Now, in order to find the solution X, we formulate what's called the Lagrangian. Now, intuitively, you can think of the Lagrangian as a way to express both the original problem and the constraints of this problem as a single problem, which can be solved in terms of the original variables and the Lagrangian variables lambda. Now, to solve this problem, we will first derive the gradient with respect to x and set it to be 0, as shown here. The solution to x is found as an expression of the known m, w, and g constants and the unknown variable lambda. Therefore, in order to find the solution x and compute it, we need to find lambda. And so the rest of the derivation is how to find this particular lambda. If we substitute x into the constraint and organize it into the constraint x transpose wx is equal to 1, we'll end up with the expression that you see here. And from this expression, we will first derive some expressions from for the submatrices A, B, and D for 2m plus 2 lambda w. This can be seen in the code, and your assignment will be to derive these expressions for A, B, and D based off of this definition. Now, there are some additional steps in this derivation. But basically, the matrix Q and its inverse Q is defined in terms of the matrix S and S of A, as shown here. And so in this assignment, you have to define the matrix S and S of A using the A, B, and D submatrices that we found in the previous step. Now, once Q and Q inverse have been defined, as shown here, according to the values of A, B, and D, S, and S of A, after some additional steps of manipulation, the expression for lambda will become this polynomial expression in terms of lambda. And so if you look at this carefully, you'll see that each of these expressions indicated in red define a coefficient in the quartic polynomial and p lambda squared. So with these coefficients, you can then use the provided greatest real root function in order to solve for lambda. And with this lambda value, the value of x can be computed, and subsequently the components of the transform can be extracted from x. So in summary, in this first part of Scan Matching Lab, we'll be focusing on implementing this update transform function. And during this part of the lab, we'll use a naive version of the get correspondence function that is provided for you. However, next time, we will cover some other tricks that will allow us to speed up the correspondence search process. Now, some key takeaways from today's lecture is that localization is an important component for autonomous systems, and scan matching is one particular approach to localization. Another kind of more general takeaway is that many problems related to robotics are formulated as an optimization problem. And as we've shown in our situation as well, many times these problems are non-convex. And so we'll deal with we'll cover how to deal with some of these non-convexities, non-convex optimization problems later on in the course. And next time, we'll cover the fast correspondence search, which is the second part of the innovations of the PLICP algorithm.